Thank you very much. My name is Matthias Peussner, and I studied applied system science in Osnabrück in Germany, and I started as a software developer 13 years ago at Rosen, and around 4 years ago I more or less switched to do things like what a data scientist does now, and I had an interest in deep learning, and that's what I will talking about. First, one slide to our company. Rosen develops and manufactures equipment, software and methods for inspection, diagnosis and protection of industrial structures. And there we do develop methodologies for non-destructive testing. And from this measurements, we get many sensor data, and we have to care about this sensor data and evaluate this sensor data so that we can prevent the damage from our customers. And especially I would talk about the inspection of pipelines, about the data which we collect during the inspection of a pipeline. So on the bottom left, you see a tool with many sensors around it, and we send this tool through the pipeline, and it collects many kilometers of sensor data from the pipeline, from the wall thickness, and from the wall. As you can see, we collect more than 160,000 kilometers per year, so we have lots of them, and one special technology I'm focusing on is the magnetic flux leakage. It works that you have big permanent magnets on the tool, and the magnet fields go through the pipe wall. And if you have some metal loss here at external or internal side, then the magnet fields changes, and we can we can measure the change in the magnetic fields. And from this, here we see a small patch of the magnet fields. From this data, we can derive the size of the defects and the type of the defects. And in this talk, I want just talk about the classification, whether it is a defect or it's not a defect. So that's the data I'm talking about, and what is maybe different to typical images or the images used in competitions. So our data looks more smooth. Here you can see a different image using a different color scheme. It's more like we have hills and valleys, so we do not have really sharp edges like we see in the pictures from the Karlsruhe Palace, for example. So maybe our data is more simple, but of course it's not very intuitive for humans to analyze them. A normal picture has the cat, for example, an RGB value, so there are 3 channels. In our case, if we take just one sensor, we have a single, let's say, grayscale image. And how real defects may look like can be seen on this picture. So they also are different from their shape and from their from their depth, for example. I talk about the investigation I've started 4 years ago, so it's pretty old for deep learning. There we ask ourselves, can we use deep learning in our evaluation algorithms? And the question, do we have enough data for it? So I started just look around and having a simple tutorial. Maybe some of you already have seen this tutorial or done this tutorial. It's a very simple one. I used this from the CAFE framework. It's Lunette MNIST tutorial. So it's classifying handwritten images from 0 to 9. And I just took over the network from this tutorial and tried to insert our sensor data into it. So it is a convolutional neural network, as it is a workhorse for most of the image data in deep learning. And of course, nowadays there are many other frameworks around there supporting deep learning, like Keras or TensorFlow. But at that time, I just took the CAFE framework. And that's how the network looks like. It's a very, very simple one. Just 2 convolutional layers, followed by a max pooling layer. And at the end, there is a fully connected layer with 500 neurons. The output is are 2 neurons. One is indicating whether we have a defect in our pipeline, or the other is spiking if we do not have a defect. And our input data is here. It's colored in with different color, but it's a grayscale image pre-processed, and we send it into the network. I took at the start, I took over the data I had at hand. This were around 840 labeled samples. So from the large image of the pipeline, we just took small images, let's say 50 times 50 centimeters. And these samples were then rescaled to a pixel size of 28 times 28. The ground truth was taken from the experts who has reported our defects to our customers, and I just took over the defaults from the tutorial. So it was drop out a batch size of 100, and it was really trained from scratch. So no pre-training was done before. Of course, nowadays, if you would start, you would also use maybe different architecture or large architectures, like this one pictures on this slide. So maybe you use a ResNet or an Inception framework, which is very much deeper than the one I used. But as I will show, I already get very good results with this simple network. So maybe it's an indication that the sensor data in our case is not just complex, so much complex than pictures of people's, animals, and other things. So one thing I have done is what did the network learn after training, and it's usual to just look at the layers, the learned layers, and I took the last hidden layer, that's the 500 neurons. I used it as a code, so the learned network encoded me the input into a 500 dimensional vector, and I put this into another algorithm, the t-SNE, well-known t-SNE algorithm. It's unsupervised, so the t-SNE algorithm doesn't get any label. And in this case, the t-SNE algorithm reduces the dimension from 500 to just 2 dimensions, so I can print all my test patches on a layer. And this looks typically like this one. We see clusters, so there has been some grouping of defects. And on the next slide I will paint all the dots. Every dot is for one input patch. Alternatively, there are newer versions of embedding or other algorithms, for example, the UMAP algorithm, which is maybe similar in the performance to t-SNE, but maybe better in the computation performance if you have more samples. So here is the embedding, and I colored the patches according its depth of the defect. So the blue one are the no defects. This is in our case the largest part. So most of them are no defects, and the other indicate the color of the color indicate the depth of the patch. And on the left side, there we have the most deepest defects, the yellow and magenta. Then we have the cyan and red ones, which are more shallow, and the shallowest defects we have here on the right. And this shows me that the network already has learned something. So the network was just trained on classification. Is it a defect or is it not a defect? But effectively, the network learned to recognize how deep is the defect. So maybe I can also reuse my learned network and use it for a regression purpose, so I can size my defects. That's maybe a nice job. So you can, instead of just painting the dot for each patch, you can really draw the complete patch, the small patch at the place. And if I zoom in here at this point where we have the deep and no defects, then you can see the typical pattern of the defects. So on the left here you see the most deepest defects, or let's say the sensor data from the defects, and over here you see no defects. The lines you can see in here are the girth wells of the pipeline. As you can also see, there's some ordering in here. Here we have a slightly different pattern than those on the left one. So the network already learned to create a feature extractor. It was also interesting, is it maybe also possible to embed those feature vectors in 3 dimensions? And I've done this also with t-SNE, and now I use an animation so we can see the clusters in the 3-dimensional embedded space. Maybe it's a little bit more space in 3 dimensions, so the clusters are a little bit better than in 2 dimensions. But of course it's harder to analyze a 3-dimensional space using a computer than a 2-dimensional space. Okay. What is also very important is during the work that I have automated all the processes. There, of course, I used Python and some batch scripts. I haven't done the pre-processing only once. So it's, as you know, you are always changing your code, trying out different things. So I'm doing pre-processing several times. I converted them. I have mixed the training data and test data in different ways, and I trained the network with different parameters. So it's good to have a really processing pipeline and to automate it so you do not have so much errors during your processing. Of course, it helps. Also, can help you prevent processing of the same processes with the same parameters. So I used the Luigi framework, so that, for example, if you want to train a network with different learning rates, but the preprocessing should be the same, then Luigi can help you that you are not executing it twice, the preprocessing. Alternatively, maybe I haven't tried it out, but nowadays there's Apache Airflow. Maybe it's also could be recommended. Okay, but at that time I have used Luigi, and it was really fun to use it. What about additional input? I also thought about how large should be the patch. I said 50 times 50 centimeters, but it could be also smaller or larger. And of course it depends on, do you have all your information on the sensor data? And it turned out that the experienced manual evaluator takes additional information into account, which is not present in any sensor data. For example, he knows which medium was pumped through the pipeline, or does the customer already has reported a special type of defects in the last few years. So he also takes additional information which is not present in the data and can use it in the manual evaluation process. If you want to put also additional information into the network, then you can just, for example, easily add additional layers in here, the red and orange one. So for example, you can add the wall thickness, maybe the known wall thickness of the pipeline as additional layer to your sensor data. Another possibility is you can add additional neurons at the last hidden layer, but I prefer to add it directly for the convolutional layers, so the convolution layers can learn from that information. Okay, what I have done at that time, I have now really split up my test data my data in 90% for training and 10% for testing. As you have seen in the t-SNE plot and the embedding, that we have a high class imbalance, so I have to duplicate the deep defects, so that I have the same amount of deep defects than the same amount of shallow defects. And then afterwards my samples were shuffled. And what I got as a result at that time is that 93% of the samples were correctly classified. This was the first result. And then, of course, the first question, is this sufficient? 39%. What if all the severe defects, that is the deep defects, are misclassified? What about wrongly labeled data in my data? And how does this performance compare to the human performance? So I had more questions after this, and I had to find answers for this, and it's not easy, for example, to find the human performance of an evaluator that is comparable to the algorithm. So at the beginning I didn't thought about what to optimize for, and it's really important that you think about your test and your test data so you can optimize for it. Another problem in my project was that, okay, I have 7% misclassified defects. How should I look at it? Maybe I can find out some systematic errors in there. But for this 7% test data, these are 580,000 samples, I need an expert which takes a look at this data. And at the beginning, I haven't taken into account the resources of an expert. So it was not... so I can recommend that you already, or that you plan resources from your experts into account if you have sensor data. I can also recommend a literature, maybe you already know it, from Andrew Ng, Machine Learning Yarning. I haven't had it around that time. It's currently in a draft version, but there are many information regarding how to design your test and your training data. So at that time, I thought about 93%, maybe can we get better? And the first thing I've tried is to use different architectures. I just changed the number of feature maps in my convolutional layers. I added a third convolutional layer. I changed the input, the pixel size of the input. And what I more or less got is a few slightly changes in the accuracy. So it was not, I didn't get very further. Of course, there are other possibilities to change your architecture. Maybe there are also automated versions now that you can use neural architecture search for creating your own architectures. Another verification I've done was a cross-validation, which I call leave one pipeline out cross-validation. So I had 840,000 samples from 50 different pipelines. So I trained on 49 and I tested on the other pipeline. And this is more or less the typical case we are facing. We are inspecting a new pipeline we haven't seen before, and we want to use the experience from the previous inspected pipelines. And the result was that we get an accuracy from 35% until 99%. And at that time I thought, oh, what I have done there. 99% is really quite well, but 35% is worse than just guessing. Of course, there may be some hidden parameters I haven't taken into account, or maybe I do not have enough pipelines or different pipelines to train on. There has to be additional thought on how to create your training data. And maybe still a problem if we have a very new pipeline which hasn't seen before and we have different characteristics, then it's hard to tackle these using a deep learning framework, for example. Some answers to the question is, of course, deep learning can tackle sensor data. You can really get fast to a solution. You can create a feature extractor just by training a simple training like classification. But you have to think about additional data you have to input into your network. And the problem is how to generalize over different pipelines. That is data you haven't seen before. So more more work has to be done in creating your training data, in creating your test data, than in how to change your network architecture. So more time is needed handling the data. Of course, there are ongoing projects from collecting from new data sets we are building up, and we thought about maybe transfer learning, and also created synthetic data. That has been a talk from a colleague last year, so it's also available in YouTube. And here are my takeaways. So it's was really easy to get started. Just take a tutorial and put in your preprocessed sensor data. Of course, signal data is maybe less intuitive for humans' perception, but maybe in this case it was, I think they are easier than natural photoscenes and animals, so maybe you do not need a very deep network. You have to think about about your ground truth, because maybe you cannot rely on human perception. And take into account the time of creating your test and your training data. I think that's it I want to tell about.
Okay, so we have 15 minutes for the questions. Anyone?
Yeah, thanks for the talk. The distribution of your labeled data is, I imagine there to be way more non-damages on pipelines than there are damages. So is there like a bias in that direction, that you have like 99% good, like well-labeled data and 1% error-labeled data?
We have, I'm not sure if I understood the question, but from this picture, most of the blue dots are the no defects in there, and the other colors are the defects. So we had a great imbalance. And for example, the very important defects, that is the deep defects with for example, a depth of 80 to 100% relative to the wall thickness. 100% is a hole. We have only just few. These are the yellow ones here. So we have to augment our training data, that we just copy the deep defects, or we have to collect more of them.
Any other questions?
So thanks for the talk. You mentioned that you had data from 50 different pipelines.
Yes.
So what I'm wondering is, there are many different types of pipelines, different welding types, different diameters. Did you take into account that these could affect your, let's say, the data of the different pipelines, and that could cause maybe some of the huge variation of your results, so that the 35% could be some, let's say, different pipeline that you didn't have in the training data?
Yeah, of course, you are right. There are some different pipelines, so we have different wall thicknesses. We have a different type of metal, and we also have different tools. So maybe also our signal data may be different because of our tools, and maybe of the behavior the tool is going through the pipeline, if it's rumbling more or less, or if we have debris in the pipeline. This has an influence on our measuring data, and this is also one reason that we had so different accuracies in that. But we have to find out which are the parameters that have the highest influence on the accuracy.
Any other questions? No. I have one question. So, in Rosen, do you guys prefer to make your own model, or you guys use the neural architecture search which you were talking about?
Didn't get the question?
You guys make your custom model, or you use neural architecture search to any extent?
In this case, we just use the existing architectures. And we haven't created, or we have adapted it to our needs, of course, but we haven't invented a new architecture like Inception or whatever for it.
Okay. One question.
Hi, thanks for the talk. Can I see the slide with the flowchart of your classification with the T's and E? I think one slide before that. Yeah, yes. Did you try, instead of the T's and E, just a basic ensemble method like random forest, to use the 500 features to classify? Because this is very interesting, but it might be easier just to use the 500 features for the classification.
Indeed, the network is trained for the classification. So there's the two output neurons who have trained for classification. But I haven't tested a different, support vector machine. So I didn't compare, for example, support vector machine to the neuron.
Thanks.
Any other questions? Okay. Thank you, Matthias, for your talk.
Okay.